In this video, we're going to explore the fundamentals of complex numbers. We will define what a complex number is, plot complex numbers on the complex plane, and learn how to add, subtract, multiply, and divide complex numbers. And when we divide complex numbers, we will need to find the complex conjugate of a complex number, and we'll get into that. So, complex numbers are used in quite a few areas of physics, most notably in quantum mechanics. But they're also seen in other areas of physics as well, and they can also help us solve polynomial equations that have no real solutions. Take this example. We've got x squared plus 4x plus 5. Now if we plot this equation on a graph, we get something that looks like this. Now you can see instantly from the graph that we've got no real solutions because the curve doesn't cross the x-axis. And if we use the quadratic formula, we quickly see that we get a negative root. But we can in fact express this negative root as multiples of I, which is the imaginary number. And we can do this by converting our negative root here, our negative 4, into a positive 4 multiplied by negative 1. And the root of positive 4 is 2. We can see here that the root of negative 4 is simply 2 multiplied by the imaginary number I. So now we can use the quadratic formula to give us a solution to our polynomial equation here. And we end up with two complex solutions. So x is equal to minus 2 plus I, or x is equal to minus 2 minus I. These two solutions are called complex numbers and are usually written with a z rather than an x. But they consist of a real part and an imaginary part. So we've got another example of a complex number here as well, where the real part is 4 and the imaginary part is 5i. So when we have a complex number in the form of a plus ib, then it's said to be in standard form. But we do have complex numbers where the real part is equal to 0. And this type of complex number is called a pure imaginary number. We can plot both of our solutions now to our polynomial equation on something called a complex plane. And the horizontal axis represents the real component of the complex number, and the vertical axis is the imaginary component. So if we consider one of our solutions now, the minus 2 plus I, where do you think this complex number will be located on the complex plane? How can we plot this? Well, we need to consider the real and imaginary components separately. So our complex number is telling us we need to move negative 2 spaces along the real axis, and by positive 1 on the imaginary axis. And we end up with a plot point here. So what about this complex number, 5 over 2i? Well, this is an example of a pure imaginary number because its real component is equal to 0. So our plot point is on the imaginary axis at 5 over 2i, positive 5 over 2i, or 2.5i. When we want to add or subtract multiple complex numbers, we need to apply the arithmetic operation separately to the real and imaginary parts. Let's say we have these two complex numbers. How do we add them together? First we write the complex sum in full. Then we separate the real and imaginary parts. So the real parts in this case, from z1 and z2, are 4 and 9 respectively. And the imaginary parts are minus 3i and plus 2i. So when we simplify, we end up with 13 minus I. So let's try and subtract the same two complex numbers now, and try and do this yourself. What's the first thing you need to do? So again, we write out the complex sum in full. We then expand out the brackets, and we need to take note here that this negative in front of the bracket is shorthand for -1 multiplied by a number within the bracket. So even though our Z2 complex number is +9, +2i, because we're subtracting it, we end up with -9 and -2i. So again, let's separate out the real and imaginary components and simplify. When multiplying complex numbers, we can use the distributive property or FOIL method, which is the exact same method you'd use when expanding out polynomials in factored form. So a quick example is, if we've got x plus 2 multiplied by x minus 3, we've got x squared plus 2x minus 3x minus 6. So let's take these two complex numbers, 4 plus 3i, and multiply it by 2 minus 5i. We can use one of these methods to multiply out these complex numbers and simplify. And when we multiply 3i by -5i, we end up with -15i squared. Now there's a useful property about the square of an imaginary number. When you square the root of -1, you get -1. So our -15i squared turns into +15. So we end up with 8 plus 15 as the real component, and -20i plus 6i for the imaginary component, and we simplify from here. Now, dividing complex numbers is slightly more involved and requires us to find the complex conjugate of a complex number. And you'll typically see this as summarized as Z star in physics. But the complex conjugate of a complex number is found by flipping the sign of the imaginary part of the complex number. So let's use this complex number as an example. We've got z equals 3 plus 4i. So if the complex conjugate of this complex number is simply the same number, but the sign of the imaginary part is flipped, what would the complex conjugate of this complex number be? So we get z star is equal to 3 minus 4i. And all we've done is flipped the sign of the imaginary part. Now, a really useful property of complex conjugates is when a complex number is multiplied by or added to its complex conjugate. So let me show you what I mean. When you multiply a complex number by its conjugate, we get a real number. And you need to remember that I squared is equal to -1. So we end up with two real numbers here because the imaginary numbers cancel out. And the same is true if we add them together. So you can see here that +4i added to -4i cancels out, and we're left with a real number. So this property is really helpful when we're dividing two complex numbers together, and this is because it allows us to remove the imaginary number from the denominator. So let's try this example. So in this example, in order to remove the complex component in the denominator, we need to multiply it by its complex conjugate. So what would the complex conjugate of 6 minus 2i be? Well, the only thing we need to do is change the sign of the imaginary part, giving us 6 plus 2i. But if we're multiplying the denominator of a fraction by something, we also need to multiply the numerator by that same thing to ensure that we don't change the value of the original fraction. So essentially, we're multiplying the original fraction by a value of 1. So now, we can multiply out the numerator and denominator separately using the previous method we just learnt. And again, we need to remember that I squared is equal to -1. So you can see in the denominator, because we're multiplying the complex number by its complex conjugate, the imaginary parts of the number cancel out, leaving us with a positive 40. And then we can simplify this answer into a complex number in standard form, with a real part and an imaginary part.